Good afternoon, ladies and gentlemen. A very warm welcome to you, and especially to our speaker this afternoon, Rachel Armstrong, and also to Madeline Jacobs, who's the Chief Exec of the American ChemSoc. It's a real pleasure to have you with us today. Before I introduce our speaker, just a few bits of housekeeping and perhaps to tell you who I am. So I'm Jim Eiley. I'm the Exec Director for Science and Education here at the Royal Society of Chemistry. And it's a pleasure to welcome you here to the Chemistry Centre this afternoon. Housekeeping. First of all, can I remind you about mobile phones? Because we're recording this, although it's not being live streamed, we are recording it, today's lecture. So if I could ask you to switch off your mobile phones, this is because it has the potential to interfere with the recording. Secondly, we are not expecting any fire alarms. In fact, the fire alarm was tested this morning. So if it does go off this afternoon, it probably means it's a real alarm. So the primary way of exiting is through the door at the back and then down the stairs the way that you've come in, and then out and into the courtyard. However, should the fire block that way, if the alarm does go off, this screen will go up and there's a door here, as you can see, it goes into the Geological Society, and you will be escorted through Geological Society and out onto Piccadilly. Just to remind you where the cloakrooms are, there are none on this floor, they're downstairs on the ground floor. So if you go back down the stairs and turn left at the stairs, you'll find the cloakrooms along on your left-hand side. And one final piece of housekeeping, I think, on your seat. You will see a feedback form. Can I encourage you to fill it in and hand it in to RSC staff members at the end, because it does help us understand what you thought of the event and how it's been run and how we can improve these events in the future. There is a free post envelope if you don't want to hand it in directly but want to return it. So if you could ask one of the staff for that, that would be great too. So today's lecture, it's a great pleasure to introduce Rachel. Rachel Armstrong is a sustainability innovator and is co-director of the Advanced Virtual and Technological Architectural, and that's not easy to say, Research Centre at Greenwich University. In 2009, she was invited to give a TED talk, one of those internationally recognized talks that stir your curiosity on ideas worth spreading. Rachel innovates and designs sustainable solutions for the built and natural environment using advanced new technologies such as synthetic biology and smart chemistry. Her research prompts a re-evaluation of how we think about our homes and cities and raises questions about sustainable development of the built environment. She creates open innovation platforms for academia and industry to address environmental challenges such as carbon capture and recycling, smart living materials, and sustainable design. Her award-winning research challenges perceptions, presumptions, and established principles related to scientific concepts and the building blocks of life and society. She embodies and promotes new transferable ways of thinking outside of the box and enables others to also develop innovative environmental solutions. Her innovative approaches are outlined in her forthcoming TED book on living architecture. So please join me in welcoming Rachel to the Chemistry Centre to give her talk, Inspiring Chemistry, Looking Through the Lens of the 21st Century Chemist to the World Beyond. Rachel.
Thank you so much for that great introduction, and it's an absolute delight and pleasure to be here, and I'm thrilled that so many people are in this fantastic library. So in 2011, in the year of chemistry, George Whitesides urged chemists to broaden the boundaries of their discipline. And he proposed that the profession needed to think boldly about big picture problems that they were best placed to solve. He also proposed that radical changes in university-based chemistry were needed to disrupt the current model so that it empowered, rather than subdued, the creative potential of next-generation chemists. Now, the biggest challenges that we face at the start of the 21st century relate to the relationship between humanity and the environment in a mutual partnership for our survival. This is not simply to do with meeting our own needs without compromising the needs of the next generations, but ways of finding about how human development can continue whilst preserving more than a recognizable degree of humanity as more people share increasingly less space and resources. We are also facing a material crisis of shocking magnitude. This is at least partly the result of global industrialized practices and modes of consumption, which over the last 150 years or so have become uncoupled from the Earth's rich processes that have forged our natural resources over billions of years. On an evolutionary scale, this material crisis is less than a second of the Earth's entire history. Or as Bruno Latour would say, it's geostory, a non-human narrative that extends back into time before the arrivals of humans and is forged by agents such as tectonic plates, meteorite impacts, microbes, and ice sheets. Yet, in this short time, the human mind and its material embodiment, its technologies, have freed our species from the diurnal grind of agrarian lifestyles. And with this new freedom, we have also shed our material responsibilities by enabling us to more efficiently and increasingly remotely harvest the Earth's resources without obligation to replenish them. Raw materials like our industrial waste exist away somewhere, out of our immediate view, for which we are not accountable. So, for example, in Far Eastern factories and sweatshops. Indeed, our increasingly technologized culture has enabled us to destroy habitats that we don't live in, guilt-free, as the consequences of consumption remain out of sight and out of mind. And it is only recently, with a spotlight on manifesting the material effects of the Industrial Revolution, with work such as Camille Seaman's work on, she calls herself a bipolar photographer, so she looks at melting ice caps in the North and South Poles, and oceanic researchers such as Captain Charles Moore, who alerted us to the cataclysmic amount of garbage in our seas, that we have begun to confront our modes of development and appreciate just how much the rise of intelligent machines has intensified and accelerated our cultural dematerialization. And over the last 150 years, social reformers such as Edwin Chadwick, revolutionary sociologists like Karl Marx, town planning champions such as Ebenezer Howard, and even industrialists such as the Cadbury family have proposed ways to establish a better balance between industrial human development and the Earth's biorhythms. The truth is, though, that until resources completely run out, our modern lifestyles in westernized countries are so comfortable that we really only seem to be prepared to tinker around at the edges of discovering new ways of finding a platform to underpin human development. Indeed, manufacturers in the East have voraciously adopted industrial methods to make their countries vastly wealthier, as they can now attack and tap resources with incredible speed and efficiency. Yet these industrial practices come at a huge cost to their populations in the form of choking skies and cancer villages. In the last 10 years or so, sustainable agendas have focused on energy and resource conservation to literally buy time, while we come up with another way of underpinning human development. Yet with businesses understanding that they can make even more profit by co-opting the goodwill of their customers and being more frugal, such as reusing bath towels in hotels, and making energy savings from more efficient appliances like light bulbs, it might appear that the ensuing age of austerity is a somewhat uncomfortable, though bearable alternative for developing new paradigms in our production practices. Perhaps in our daily lives, we may even be persuaded that there really isn't much of a problem at all, provided we are more prudent about our consumer choices. However, uncomfortable events away from our domestic sphere, such as rapid loss of Arctic ice and more turbulent weather conditions owing to the knock-on changes in the jet stream, speak of the continued urgency of our longer-term goals. Indeed, as we develop more efficient ways of using non-embodied resources, such as energy, we are further persuaded that business as usual is still possible. However, if we open up the taps on freely available energy, we do not change the developmental paradigm. We still consume matter and leave it in forms that are ecological dead ends, such as the recent uncovering of rubbish dumps that are growing even in the abyss. The biggest challenge of our 21st century is to reassess and reconnect with human development and the material world, and elevate the status of matter in our cultural and economic discourses. Yet this conversation is not going to be productive without chemists championing the cause of the material world and showing us its full potential. And whatever the specific vision of 21st century chemistry may be that appeals to scientific discovery, such as making life in the laboratory, or finding out the potential of graphene, the cultural agenda that chemical discoveries need to speak of is our shared humanity, especially as the distribution of resources becomes increasingly unequal. To date, modern chemistry has largely dedicated its insights towards supporting existing manufacturing systems, for example, by creating increasingly more innovative industrial products, such as plastics that can conduct electricity, liquid crystal displays, synthetic bioactive molecules, food preservatives, refined fuels, and a variety of surprising nanoparticles. With the health of the environment at the heart of our global cultural agenda, chemistry is not well positioned to be one of the good guys that could, for example, invert existing paradigms whereby making something could conceivably be good for, rather than bad for, the environment. Indeed, Rachel Carson's legacy of Silent Spring, which painted an industrial soiled vision of nature that was not quite fatal, pointed the finger firmly at the chemical industry as being responsible for the carcinogens that found their way into our air, water, soil, and food. And although industrial manufacturing plants have gone a long way towards being more environmentally conscious, their practices are not perfect. Indeed, from a cultural perspective, the spectre of old manufacturing processes hover around the chemistry profession like Jacob Marley's ghost, and where ecology is involved, chemistry is not generally thought of as being part of the solution, but situated at the heart of our problems. Indeed, the association between chemistry and manufacturing is so tightly coupled that students who express an interest in the subject can be expected to be handed introductory literature that is emblazoned with tidy, goggle-cladded, white-coated wearing chemists, often intensely scrutinizing test tube contents. In fact, the fundamentally analog nature of chemistry may even be off-putting to the digital native generation who've grown up in a world of endlessly morphing geometries that are not at all limited by the material world. Indeed, in some ways, the information technology revolution has been a kind of anti-chemistry. It is free of the limitations of material constraints and allows us to literally reimagine the world in the way we want it to be. In fact, the very freedom that the digital technology has given us to reflect on reality means that it's become an integral, if not necessary, part of our thinking. The digital domain has also been a huge success for its investors, which means that society at large turns to cyberspace for inspiration in addressing just about every solution, ranging from, is there an app for that, to big data and the corporate utopia of smart cities. Of course, chemistry has benefited from the digital revolution, by constructing building blocks of our ubiquitous digital gadgets with new plastics, metals, silicon circuitry, and batteries. It also makes use of software to visualize complex chemical data sets and even design new molecules. However, models are not formal material solutions, and digital wisdom is only part of an approach. While computing has made our industrial processes smarter, faster, more efficient, and cheaper, we have fueled these developments by resource consumption rather than, say, resource transformation, which is something that, of course, McDonough and Branner promote. While governments are trying to convince us to consume less and be more efficient with our resources, this approach alone is simply not going to be radical enough to deal with the extra demands made by 2 billion more people that will be on the planet in the next few decades. It is more pressing than ever to do things differently, not at a virtual level, but in the real world. But before we can do this, we need to change our expectations of the material world, which means elevating the status of chemistry. For chemistry to be as prestigious and as investable in as digital technology, then the role that it plays in our cultural development also needs to change. Chemists themselves need to be regarded as part of the solution to our global problems, not responsible for them. Yet the role of the chemist is still equated with being a cog in the industrial machine. Moreover, the life that chemists are imagined to lead is as a solitary, indoors environment confined within white walls, a bit like laboratory rats. Indeed, their personalities are not only hidden behind walls, but also behind white coats and other protective garments, which not only separates them from their experiments, but also from society. To appeal to next generation chemists, it is vital that the profession is equated with environmental and cultural advocacy, like climate chemists, but not only by recording environmental change, but also by proposing and demonstrating alternatives and interventions. Now, although not many school children want to be industrialists, who are viewed as the bad guys, many young people do want to help save the planet and be one of the good guys. Frankly, the industrial image of chemistry and any other industrial practice does not speak to the concerns of our time, or more importantly, to the next generations of chemists. In an epoch that is concerned about nature and the environment rather than its conquest, which fueled the modernist agenda, the association between chemistry and artificiality further alienates chemistry from the public and also from funding. Yet the natural sciences have managed to stimulate cultural debate and discussion about their core issues, such as genetic technologies, by allying with bioart in iGEM competitions. And the physical sciences have wooed the world with the drama of the Higgs particle and charismatic television programs on the cosmos. However, chemists, as Whiteside observes, have still yet to establish their cultural identity and core research agenda for the 21st century. Perhaps because of the industrial image of chemistry, governments are looking to the natural sciences as a first-choice partner with the digital realm to restore a sense of material order of the world and repair our relationship with nature. For example, governments are supporting advances in genetic technologies to feed populations and more efficiently produce biofuel. Yet bioprocessing alone is simply not low-level enough to make the kind of difference we need to make in order to move away from industrial practices. We need systemic changes in the way that we imagine the world, but also in the way that we build it too. At a fundamental level, chemistry is positioned perfectly to deal with the biggest challenges of our 21st century. Chemistry is more than a science that can help us draw together the two threads of thought that Blake charged Newton with when he drew the alchemist scientist as a godlike figure, preoccupied with the mathematical laws in front of him and unobserving nature behind him. Chemistry may also help us deal with new forms of technology outside of the industrial model, for example, through natural computing practices, a term inspired by Alan Turing's interest in the computational powers of nature, where materials at far from equilibrium states can make decisions based on complex information and respond to them in real time, for example, through pattern formation and other lifelike behaviors. Indeed, with new kinds of technological platforms, chemistry moves towards a practice that can act in the social realm beyond the laboratory setting and may even begin to take a central role at the heart of our cultural agendas. So chemistry is more than a substrate for machines to work on. It is a transformer that unites us all through the interactions between many species of stardust. More ecologically integrated ways of living may be possible by appreciating this common ontology between human, non-human, and even the non-living world. Indeed, this connection between animal, plant, and mineral was recognized by Linnaeus. Yet classification systems have largely neglected the association between minerals and biological systems. For example, lifelike chemistries do not yet have a formal classification scheme. And yet a range of commentators over the ages, from biochemist Vladimir Vernadsky to philosopher Manuel de Landa and architect Lebbeus Woods, remind us of our complex entanglement with the mineral world, which should cause us to rethink the cultural status of matter and its language based in chemistry. Philosophically, traditional Western thought has positioned the material world as passive, brute, and inert. In other words, the lessons from chemistry, where substances are fickle, responsive, and willful, are largely omitted from our cultural agendas, except perhaps in the case of foodstuffs. Yet chemistry is far from inert. The dynamic, even strange qualities of chemistry are shaping the technology that underpins our modern lifestyles in substances such as plastics and rare earth metals. In these incarnations, chemistry is anything but obedient and predictable and has an agency to be continually negotiated with. However, cultural entanglement and public accessibility do not imply dumbing down research into pointless truisms, as these are the favorites of broadcasting corporations as a way of summarizing the contents of science educational programs in a soundbite. You've probably heard them. Biology is amazing. Astrophysics is very, very big. And chemistry? Well, it's everywhere. Yet chemists need to communicate proactively about the character, vision, and opportunities that their profession embodies. Otherwise, others will fill the void for them. So, how might 21st century chemistry build an accessible vision that connects with an environmentally concerned culture, not as a top-down solution for something, but as a joint project between chemistry and the public, which can excite generations of potential chemists and people in the community yet to come? Although Whiteside's calls for big picture challenges, and this is a very pertinent and pressing situation, the priorities for the future of the chemistry profession and what society needs is actually not yet clear. Perhaps 21st century chemistry may even dare to break the tradition of identifying as an expert-centered practice and start to understand its collaborative identity to forge mutually reinforcing alliances between stakeholders. By this, I don't mean decision-making by a committee in order to decide which grand scheme is best, but by chemists experimenting and exploring new possibilities in a growing world as a professional practice and as a collective project with other disciplines, which may produce many different kinds of cultural impacts. And this is not a utopian vision of how different knowledge sets and methods may interact. Difficult and paradoxical ideas and relationship require continual management and negotiation to facilitate the potentially disruptive outcomes that may emerge from novel juxtapositions. These may be enabled by shared visions of what those possible transformations may be, or indeed mean. To develop this idea further as a near 21st century chemistry practice, I will share some of my collaborations in the field of architecture. I'm based, as was said, at the School of Architecture, Design and Construction at the University of Greenwich, where I combine architectural design, which works at the human scale and upwards, with a study of lifelike chemistries, which function at the microscale to the centimetre scale. My work investigates whether and how incorporating more lively materials into our living spaces may change the quality of our relationship through architecture and humans on the environment. I will draw on three areas that offer challenges and opportunities for 21st century practice. Firstly, synthetic biology, the synthesis of lifelike systems. Secondly, scale, big like us. And thirdly, multidisciplinarity, or working together. So in 2009, I began working with the Büchli system, first described by German zoologist Otto Büchli in 1892, where he added potash to olive oil. Büchli observed that the oil field broke up and spread out into finger-like extensions, which supported his theory that protoplasm was fluid in nature. In fact, Büchli wondered if he'd invented an artificial cell, a protist, or an amoeba-like creature, and documented his findings as drawings. When I came across the Büchli system, there were no photographs in the literature. In fact, the simple saponification reaction appeared to have been largely unexplored. So Büchli experimental conditions were recreated using 3 molar sodium hydroxide and Manini extra virgin olive oil. Now, on adding a 0.5 molar mil drop of sodium hydroxide to the field, olive oil field, it spread out as described in the Büchli experiments and broke up into the millimeter scale droplets that have been described. Now, although the process was visible using the naked eye, I studied the droplets under low magnification, time-4 magnification, and observed striking and unexpectedly lifelike behaviors. Now, although the process is effectively based on the production of soap, the droplets had novel properties that didn't have very easy explanations. Here you can see that, I don't know whether you can actually see it because it's quite light in here, but essentially you have droplets that are about 1 millimeter in diameter of sodium hydroxide that seem to work together, hang out together, and then they communicate in a way which is very reminiscent of the quorum sensing of bacteria, except rather than attracting each other towards themselves, they're actually dispersing in this field. And what's very interesting was that this showed that these droplets could actually be regarded as having a body, and not a membrane, but an interface, so they consumed and modified their surroundings directly. Instabilities at the interface also produced polar system with a distinct head and tail end, and potentially these droplets could act as dynamic carrier systems for the spatial distribution of matter. But the millimeter scale was just too small to work with by hand. An opportunity arose to develop the scale of the system from a laboratory into a public setting, in collaboration with architect Philip Beasley for the 2010 Venice Architecture Biennale. So this is the Hylozoic ground installation. It's a giant cybernetic installation, about 19 meters by 3 meters by 4 meters, that audiences can walk right into. And in that matrix, the various mechanical components, such as swallowing tubes and feathery fingers, tickle you and follow you around, but not in a reactive way, so that it's a very simple relationship between response and stimulus, but actually in a very complex and kind of surprising way, which is done through a neural network that was designed by Rob Gorbet. Now, the Hylozoic ground was a site in which I could introduce the living chemistries into discrete vials, and they were left open to the air. But I firstly had to modify them so that they could actually be seen by visitors attending the gallery, because remember, they're about 1 millimeter big in the laboratory. So I created a retardant, essentially sorted out some soap-like products from the actual reaction itself, added it to the sodium hydroxide, and got a much attenuated response of these droplets. Now, of course, the lifelike properties aren't exactly the same as they are when the droplets are a lot smaller, but over the course of 3 months, these droplets were responding to levels of carbon dioxide in the gallery. And they could be actually regarded as being a kind of smell or taste sensor within the body of this giant cybernetic framework, simply because they could respond to carbon dioxide and literally smell or taste the people in the laboratory. It was a notional idea, but it was a way of demonstrating how a different kind of technology might actually have a social interface. Now, this installation was modified again for the Vienna Natural History Museum. And this time, an additional constraint was placed upon the system. It was actually squeezed in between 2 centimeters thick of glass. And a very interesting thing happened. It started to spontaneously produce Turing bands. So this was actually quite a surprising event. Of course, Turing bands are Alan Turing's morphogenetic explanation for how leopards get spots and zebras get stripes. And it was just very interesting to see that on a chemical principle that this was actually possible to produce using a dynamic chemical system. So these experiments inspired ideas about environmental pharmaceuticals that could, for example, remediate the effects of pollutants in the Venice Lagoon, which was discussed with the European Centre for Living Technology. And further applications were explored in the Cronin Group, the University of Glasgow, in the possibilities of carbon dioxide eating paint. So these were designs that were drawn by some of the architects. So this is drawn by Dan Slavinsky about solar panels that were incorporating protocell-like fluid systems as charge carriers within chemistries that could trap sunlight. Since Bucci droplets had to be made by hand for these meter-scale installations, the possibility of developing a different kind of production platform was explored during a wet fab workshop with the Cronin Group. This is really just a demonstrator photograph here. We've got sodium hydroxide and copper sulfate in the pistons, the syringes that are in the 3D printer. And also it was an experiment where we were trying to experiment with the consistency of these solutions, because obviously as soon as you've got a hole at the bottom, you're really not in control. And when we designed this system, it was in a multidisciplinary environment. I brought an artist, Julius Popp, who actually designs with fluidic systems. He's done some incredible work at MoMA called Bitfall, where literally a giant printer can write letters using water droplets. And so this became an environment where we actually started to bring potential design applications with the science and started to imagine what these kinds of possibilities could mean. So embodied droplets that can distribute matter in time and space may enable the development of new ways of linking matter to information. For example, Gabriel Viller's work at the University of Oxford uses vesicles to form functional chemical networks and may be of value to the next generation of 3D printing techniques. Also, dynamic droplets may help us use resources differently, as in Hylozoic ground, where carbon dioxide was transformed into a vibrant indicator of human presence and even contributed towards microstructure growth in osmotic formations. Yet the development of self-assembling chemical systems required widespread infrastructural changes if they're to fully deal with the spatial conditions that they're necessary in. For example, with the first algae facade built by IPA Hamburg and Arup, perhaps self-assembling chemistries will be able to benefit from more vascular forms of distribution like macrofluidics channels in buildings that enable these spaces to possess physiologies by linking bioprocessing systems together. So essentially, we're starting to scale up the possibilities of dynamic chemistries and synthetic biologies and indeed kind of garden biologies within social spaces. And these are pioneering projects that are actually starting to be realized and used in the context of sustainability. So whilst the impacts of chemistry are typically imagined at the human scale or contained within it, the ecological agendas of global concern are coaxing chemistry to explore new scales of impacts and challenge us to imagine how chemistry might work more broadly and directly in society, not as manufactured products, but as entire systems of organization, like giant natural computers. So developing the Bucci droplet idea further, an architectural project was proposed to grow an artificial limestone reef underneath the city of Venice, which stands on wood piles. The idea was to use a droplet system as a way of utilizing local materials differently, specifically dissolve carbon dioxide in minerals and fix them into solid structures. So using DEP, diethyl phenolphthalate, as a carrier and grinding up soluble calcium salts in the oil, a very simple demonstrator system was produced where a calcium carbonate shell was formed around the oil, which acted as a site for precipitation. Other work on the droplet shows that they can be given metabolisms that enable them to shed skins, as in this benzene and anhydride system here, or even move away from the light, as in this system here. So these droplets served as architectural models for a formal system, which is still to be developed. The proposed technology will be based on dynamic droplets that incorporate an optimized oil carrier capture system and a cation capture system, and photosynthesis metabolism. Since Venice is a UNESCO World Heritage Site and also has very murky water, it was not possible to test the droplets directly in the lagoon. So working with Red Bull, the model droplet technology was made accessible to a group of Venetian architecture students who observed how the chemistry could rapidly produce vigorous white shell-like structures when added to samples of Venetian water in large Petri dishes. These outdoors experiments not only challenged ideas about what a chemistry laboratory could be, but they also opened up the ecosystem as being a direct site for exploration and discovery, rather than simulating abstracted systems in controlled settings. Yet this does not mean that one model of experimentation is better than the other. It simply means that more options are available to inquiring minds. So this project has many speculative elements that help navigate an extremely complex set of conditions that need to be addressed for the possible development of smart concrete-like structures. Yet even in the early phases of development, the ongoing research is valuable, as by bringing architects together with chemists, it's opened up further fields for research and development. During our research, we developed architectural models that could work iteratively with chemical experiments to continue to develop the idea of a self-assembling reef-like structure underneath the foundations of the city. Although these ideas and experiments are not near to completion, they continue to be regularly critiqued and modified. So as the technological proposal matures and the Venice project aims to work more synergistically with the marine wildlife, which is being regarded as a potential co-constructor of the reef-like system, an even greater range of partnerships are anticipated. And pertinently, Tiatini et al. Have proposed to lift the city anthropogenically by inflating the aquifers with seawater over the next 10 years by a foot. If this project goes ahead, it means that there is a need for smart concrete, which can coat the wood piles to stop them rotting as they become exposed. And they would be needed to be tested alongside the changing lagoon ecology as the Moses Gates are raised in 2014. In this sense, the reef is not only a form of coastal jewellery or marine garden, but also serves as an ecological barometer of change. My collaborative work is fundamental to my research practice, and therefore my project work is not driven by questions that originate from any single discipline. Yet my work has a common theme, which relates to how materiality may reinform the way that we design and construct our living spaces. Not only are different disciplines key to my experimental work, but I also work with different methods and forms of evaluation. Indeed, my research inevitably spans the two cultures and STEAM, science, technology, engineering, arts, and mathematics. And arts are at the core of my collaborative partnerships. In fact, the arts and humanities play a key role in the innovation process as they stimulate culturally appropriate ideas towards which technological developments may be directed. During this research progress, the project may be effectively articulated by producing models and drawings that are visually engaging and serve as powerful communication tools. For example, the Future of Venice project has benefited greatly from Buchley droplet installations and drawings made by Christian Kerrigan and GMJ. By working in partnership, in a methodology that Isabel Stengers describes as an ecology of practices, it is possible to create forums that encourage radical forms of new partnerships based on shared interests. Researchers from many disciplines can here dream along with each other rather than jousting for the most prestigious position in a hierarchy of truths. The Avatar Group has been developing a format for collaborative practice since 2009 based on a 2-day event where researchers from different disciplines present their work around a particular theme on the first day. And on the second day, the collaborators are in a moderated workshop where they develop proposals for very specific questions and ideas. So events have included eclectic systems architecture, architecture and complexity, unconventional computing and architecture, artificial life and architecture, wet fab, Future Cities and Future Cities 2, which was a collaborative work on the design of living interiors on a world ship with rocket scientists, one of whom is in the audience today. This collaborative platform offers researchers time and the opportunity to talk freely with each other and begin to climb inside each other's shoes to understand the world from another perspective. Indeed, these workshops have led to groundbreaking innovation work. For example, the wet fab collaboration with Lee Cronin led to the production of a system that can print any medicine. Chemistry has the potential to change the world, and enable us to inhabit it in a very immediate way. And whilst there is a great value in traditions, there are even greater possibilities in what comes next. And how we structure and shape these for the immediate present and for the generations of chemists yet to come is still yet to be written. But since I am a multidisciplinary practitioner, I'd like to introduce a non-chemical technique that may or may not be useful when you're thinking about the legacy that the Royal Society of Chemistry or chemistry associations will forge for their future chemists. I've therefore written a manifesto for 21st century chemistry to stimulate those conversations that Professor Whiteside is asking for us to hold. And for those unfamiliar with the production of a manifesto, these documents are written when we're trying to challenge the status quo, when the outcome is not already known. Each manifesto is for something and against something. Yet it does not propose to resolve challenges, but helps to shape a vision as a kind of avatar for something that has not yet taken place. In any case, this manifesto is not designed to instruct, but serve as a provocative tool, an aid in decision-making as you individually and collectively reflect on the future of your profession and how you may help society at large better relate to our material world and ultimately promote our continued survival. So Manifesto for 21st century chemistry against a hermetic practice. This is going to sound strange to chemists probably. We recognize that chemistry is the substance and discipline that unites. Through chemistry, we share a common ontology with all matter through stardust. In this community, substances are more alike than different and seek an epistemology that connects, not divides. Chemistry is a transformer, capable of countless acts of computation which operate within definable limits of probability that are shaped by time's arrow. The language of chemistry shapes the medium through which new relations can be built and fostered. Chemistry is a discipline that integrates with others by identifying overlapping interests in material effects that form the basis for new synthetic partnerships and projects. Chemistry is an ecological discipline. Chemistry is integral to the physiology of living things. Oxygen is much a part of our breathing system as our lungs or a tree. Chemistry does not seek to erase its rich history, but to incorporate its lessons and discoveries into a continually evolving living practice. While the laboratory has been the traditional site for chemistry, where substances are distilled and smelted to yield their secrets, 21st century chemistry, I've done something here. Go back down to here. There we are. 21st century chemistry may be meaningfully researched and explored in its native complex states without the need for a formal laboratory. Chemists translate and communicate the secrets of matter at all scales, from the truly minuscule to the mega scale, so that we can culturally understand its importance and impacts on our daily lives. Chemistry is diverse, open, collaborative, and entrepreneurial. It is the master, not servant of industry, and has the power to shape the material connections that form our production platforms and manufacturing systems. 21st century chemists are clothed in many lively patterns and wear all the colours of the rainbow. Chemistry is inseparable from and accountable to its philosophy and cultural agendas. While adopting objective approaches in measurement and analysis, chemistry remains subjectively concerned and undetached from the consequences of its insights and findings. The study of chemistry may reveal new possible relationships that we can build and establish with the material world so that we are better connected with our terrestrial biorhythms and potentially establish forms of human development that do not damage or reduce the material complexity and networks of exchange in the substance of our planet, but enriches them. Chemistry can and must save the world. Thank you. I bet that did sound strange.
Thank you very much, Rachel. We'll be taking some questions now, so if anyone has a question, please just raise your hand and we have a microphone for the recording. Don't be shy. Someone break there. Thanks.
I have a comment and then a question. The comment is that I think in the beginning you were a little unfair towards chemistry, because chemistry, of course, provides all of the materials that you use for all of the devices of the 21st century, and you couldn't be anywhere without it because everything is made out of chemicals. That's the comment.
Yes.
The question is, how do you explain the large increase in numbers of people wanting to study chemistry if it is falling so far behind physics and biology?
So I'll respond to your comment first. I mean, the provocation is that in the cultural imagination, and in fact, I mean, for most of us, we are stuck within an industrial model of practice, whether we like it or not. And essentially, it's, I mean, like the Manifesto, is simply a provocation to actually critically think about the kinds of models of production and kind of intervention that we're actually promoting when we go about all of our daily practices. The rising chemists, I read different literature which kind of says there's a fall in students doing STEM, particularly students. So I think that, female students. So I mean, I'd like to see the figures, but it would be very interesting, and I'm very pleased if there are more students doing chemistry.
Comment on the gender balance.
Yeah.
I mean, the gender balance in chemistry is more or less exactly 50-50. It's just about exactly what it is in the population as a whole.
Okay.
Thank you. Was your manifesto tailored for this audience?
Yes.
So the frequent reference to chemistry is for our benefit. Do you distinguish chemistry from science in the 21st century?
No, I mean, I think it's a manifesto for the 21st century, and I identify chemistry as being specifically the guardian of the material realm. So yes, it's a cultural reference rather than a way of dividing science.
In terms of chemistry in the built environment, having been involved in civil engineering and in chemistry, the saying is that if you've got anything that is rubbish or waste material, you put it in the roads or you put it in buildings. I mean, what has been happening for the millennium is that we build things out of materials that are locally available. And chemistry has influenced a lot of these dramatically in the last 100 years in improving these materials, like things like concretes and asphalts. But I don't see anything dramatic coming in terms of the basic material that we're going to build our structures from.
I mean, but building techniques haven't really changed since the Victorian times. I mean, we still pre-manufacture objects and then assemble them, under equilibrium conditions, to construct a building. And our materials, other than plastics, really, are indeed very similar. I guess my provocation is about the way that we build, the way that we imagine our solutions. And whilst we are definitely making progress in having different kinds of industrial practice, that there is a need to think about what it means to design and engineer ecologically. Is it just a form of material and energetic conservation, which I think sits still within an industrial framework? Or is it actually something else? So you're absolutely right. We're still doing what we were doing 150 years ago and probably before then. And our materials fundamentally haven't changed that much. Now, that doesn't mean that that's wrong. What it means is that the practice could be considered with 21st century insights as being incomplete. So that, rather than saying that everything that we've done up to now is wrong and rubbish, it is simply a way of saying that perhaps there are ways of thinking differently about what we're doing and finding spaces for innovation within those possible chinks in practice.
I'm one of these. Can you hear me? Yeah. I'm one of these people who I'm teaching chemistry to very young children, anything from 8 to up to 18 as a private tutor, and I visit children in their own homes, and it's quite interesting after having been a school teacher to see how different young people are often when they have an opportunity to speak to me, a chemist, a sort of an older person, and have a chance to sort of air their misconceptions and their misunderstandings about things, and often it's just an opportunity to talk to somebody for an extended period of time. And I think it's very important to try and inspire young people to practice chemistry through trying to get opportunities established whereby they can talk individually to scientists on a sort of relaxed basis. And that's one of the things I gain when I teach them in their own home as opposed to in a school. The other feature that I have come to learn is that very young children, I'm talking children sort of below the teenage area, still don't have the opportunities to muck around with materials, should we say. It's still not something that's encouraged, doesn't seem to be encouraged by their parents for all sorts of reasons. I'm talking about, perhaps playing around with materials in the garden, in the alley, getting dirty, getting wet, maybe even hurting themselves sometimes, to try and understand materials and know their properties and want to master them. Now, that sort of basic drive is missing, and I'd like to see society change whereby parents would be more encouraged to let their children loose, as it were.
I think that the IT revolution is very seductive, so that, my daughter will sit for hours on the iPod, and she does go and do some cooking, but that's about as far as she goes when it comes to getting mucky. So I think it's very interesting. I think that there is a kind of cultural pull. Certainly when I was little, I would be in the back garden playing in the soil all the time. So I agree with you. I think that kids should get muckier.
There's a question in the back, and then Victoria, back first. There is a question in the very back as well. Oh, okay.
Basically, to follow on from the last point that was made, the problem you have with encouraging kids into chemistry is basically there's too many lawyers. We need to get rid of the lawyers. No, I mean that quite seriously, because the problem is society has become far too risk averse. And kids are not mucking around with chemistry anymore. I speak as someone, I was given a chemistry set when I was 5, and it was the best thing I could ever have done. I was causing mayhem and disruption. But as a result of that, it carried through my love of science. And kids don't get that opportunity anymore because we stop them from playing around with things. We tell them they can't do it, it's too dangerous. Well, they'll never learn unless they get that opportunity to be inspired themselves by actually making exothermic reactions in the kitchen and things like that. So that's what needs to be done. You need to get rid of all the risk-averse problems in society.
That's a great point.
As a member of the Royal Institute of Chemistry and Chemical Society, and now the Royal Society of Chemistry, been around for 50 years, we, according to our mottos, ratio ad causas, which was DRIC, reason based on observation and practical skill, and now pro scientia et humanitate, on behalf of civilized knowledge for humanity, mankind and life, we must regard ourselves of servants to the planet.
Thank you, yeah, absolutely.
And who was the best or is the best synthetic chemist ever? Synthetic organic chemist ever? God. Solar power.
Fred Key, I solidly thank you for opening our minds to a problem and a potential problem which is not caused by chemistry, but caused by negligent chemists, perhaps, because chemistry can also be the curative of nature and for nature, and I've used it as such in my experience throughout industry. I also support, this is separating ourselves from the main subject of your dissertation. Some of our last speakers who bemoan the fact that our young people are not getting the proper opportunities and proper incentive to learn chemistry, and I thoroughly support it. My first contact with chemistry was an American chemistry set. I still remember the brand, Curtis. It did not have any hazardous experiments in it, but certainly was some level of saponification in it, which is topical, and a lot of color making, which really fascinated me. And I went on to not only study chemistry, but also experiment at home and do some quasi-dangerous experiments with some good friends. But I think that is lacking, yes, seriously lacking. And health and safety has gone mad, both at school and in industry. And that ought to be rethought, I think. The other thing that a lot of... Anyway, thank you very much. Really appreciate this mind-widening dissertation which you've given us. Has really expanded our way of thinking about chemistry and its applications.
Thank you.
I think there was a question here first. Do you have a question?
First of all, I was under the impression that cookery was chemistry with a bit of arrangements, but I feel as one's got to be very careful between talking about chemistry and then technology. A lot of the stuff that you have here is technology, in other words, application of. Exactly the same way as the Science Museum is really a technology museum, and I think it could get bamboozled. But chemistry, or science, all of it, the basics of it, I think, are extremely difficult to understand those concepts. Playing is fine, but then how to understand concepts is extremely difficult. And unless you've understood them, you can't then develop. I don't know how you get concepts understood quickly, easily, because they ain't in exactly the same way as if you want to become a tennis champion. There's a hell of a lot of hard work behind the scenes, and that the science and the understanding of all the various sciences, to go from what is play to understanding so that you can take it further to be able to do a lot of the things you talk about.
I think that's a very important point. I'm certainly not advocating that, that there is no need for a specialist discipline. Essentially it's about creating a platform for connecting. The traditional and formal study of chemistry, the way that it's currently being done, I mean, is absolutely excellent. I mean, essentially, I guess the question I would like to ask is, what other ways, so how can that specialty connect with others? I mean, so for example, with the architecture profession, who knows nothing about chemistry, does not propose to be a chemistry expert, how can architecture benefit from a synergistic relationship with that level of knowledge? It's not to say that, we need to dilute down the chemistry curriculum or anything. It's simply about getting used to building networks, which is what's happening with the digital platform. The digital platform and the digital natives think about connections between things. So they think, oh well, chemistry is relevant to what I'm doing. I'm not a chemist, but how do I then work across that discipline? How do I start to forge a relationship that actually may bring new insights and opportunities, because you're creating that applied, a space for applied knowledge. And I absolutely agree with you that what I was showing is technology and not chemistry, as a kind of a specialist science. I set out to find ways of applying an interesting system to many different contexts and kind of running with a story of possibility to examine, I guess, innovation. What does it mean to innovate collaboratively? What does it mean to have an open platform? Did it create conflict through somebody getting upset about notions of IP? But it didn't actually, because the technology itself was actually at a very early stage of development, and so there was no constraint, as it were, no industrial constraint for a product to come out of those relationships, but there was a great deal of sharing of knowledge. But I think the interesting thing is iterative processes. I don't think that collaboration works when people don't know what they're doing. I think it works when you have people that are expert and the best in their fields working with others that are expert and the best in their field. That becomes very interesting. So it's not done blind at all, and partnerships are very carefully curated. So totally agree with you and totally respect the kind of the integrity and the kind of the depth of knowledge that is in the chemistry profession.
I may have missed this point that I'm trying to elaborate, but I would like to know if you have had any chance of putting this into practice. I understood this as a conceptual thing, and I would like to know if it is in practice at the moment, or at least in trial runs as well. So.
Yeah, so there are a couple of, so I mentioned that the Cronin group have got IP on a smart paint, as it were, based on the idea that a paint can eat carbon dioxide and change colour when it's full, which was inspired by the micelle-based technology, as it were. So that's one possibility. We're also working with Autodesk, which does does software modelling, to try and start to create a model to understand how those dynamic processes are working. So we're working with physicists and mathematicians in order to understand some of those DNA-less life-like structures. And maybe by creating that kind of sense of parallax, we'll understand what's actually happening in those processes. So I'd say that those two are the biggest kind of real outcomes from the experiments. But I think when you are combining fields it's a bit like life. You'll get a lot of different life forms, and maybe only a couple survive. But I think that it's something to do with the culture of our times, that there is this desire and possibility to connect, because we are rethinking the cultural frameworks in which we're inhabiting. We're starting to see blending of cultures and geographies and information sets. And we're studying alongside people at university, that have very different worldviews to our own. And so in some ways, it's a small model of a much greater kind of cultural condensation of different ideas, beliefs, and practices, and working out how we can actually take that forward in meaningful ways.
It probably brings it down to a rather mundane level, but who funded those multidisciplinary experiments?
That was all done on the basis of my EPSRC grant.
Good old EPSRC.
Actually, my question was really quite similar. I'm just wondering, how much is this sort of thinking beginning to change funders' minds? Are you getting significant support from major corporations and from major organizations in the UK and elsewhere?
I think changing corporations' minds is a slow process, and that most of our work is done by sheer willpower and enthusiasm. However, yes, there seems to be a desire for change. If you listen to Mark Miodownik on BBC4 talking about smart materials, he'll start talking about living buildings. Working with people like Autodesk, Arup, which is a construction engineer. They've provided support in kind. We are negotiating something with Unilever at the moment. So it's essentially, keeping at it and demonstrating that what we're doing has value, even if it isn't as a product, that there are, I guess, innovation opportunities in the process that are starting to create a potential market for change. So I think that the value of humanities and arts in innovation is that it almost like pre-does your market research for you. So if you think about the traditional innovation cycle, which is you create a thing and then you build markets around that and try and push it out through advertising to make your audiences think that they need it. Well, in some ways, this is a non-traditional way of thinking about innovation, and I'd cite the production of victimless leather as being an example. So in the year 2000, Symbiotica came up with this idea of victimless meat, and they did an arts installation that was shown in New York, which proposed that, using tissue cultures, we could actually do all the things that we expect from, cow flesh. Now, that got run with in various different ways with various different research groups. I mean, so there was the kind of the cow-free burger, I think, the 150,000 euro worth of fast food. So a number of people looking at this idea as being something that was exciting and as being a vision that they would like to see happen, because the idea of it was culturally right. This year at TED, a young man called Andras Forjaks has set up a corporation that's now making synthetic leather. And he's literally, very much like yeast. It's not transformed cells. It's literally like a yeast culture. So he's got meat cells in there. And he literally grows these layers that are now different forms of leather. And there are designers absolutely queuing up for these small squares of leather. It's very boutique. And so there's a market there already, and nobody needed to do the market research as to, how many people, were going to use this product, and actually, was it something that was going to make money in 2 years, 5 years, 20 years. So I think that, I'm not saying that, again, I think that we're looking at different models coexisting. This is not about, out with the old, in with the new. It's actually about ways of coexisting where frameworks may be very different, and figuring out ways how to change your frameworks so that you can, I guess, more nimbly navigate challenges and spot opportunities, not only just for the research development, but also spotting, where you may get funding from. Because now, a great source of funding is crowdsourcing. If you've got the time to spend your time on Twitter and Facebook. But people are getting significant revenues now to develop ideas that otherwise you just wouldn't get through a central funding body.
Other questions? We have a few minutes still. If there are no more questions, please join me thanking Rachel Armstrong again. Thank you. Thank you very much. And I just want to invite all the RSC members to join us in the science room downstairs at 5 o'clock for our annual general meeting. Thank you, Rachel, again.